Hey there. So in this video, I'll be going over the MobileNet's paper. Reading research papers is extremely important, especially in the field of machine learning and deep learning. Because the field is so fast paced, it's important that you can pick up a paper and read it yourself. Because many times the ideas aren't covered in courses, articles, or blogs, so you should be able to pick up the idea without their help. And reading papers can be especially difficult if you're a beginner because there may be so many terms that you don't know about. And sometimes writers they phrase certain ideas or some details in somewhat abstract or ambiguous ways because they don't want people to exactly copy what they're doing. So hopefully this video will not only inform you what a mobile net is, but also get you more familiar with research papers. So let's look at the abstract. So the abstract is just a broad overview of what the paper is presenting. So in this paper, they present a class of efficient models called mobile nets for mobile and embedded vision applications. Mobile nets are a streamlined architecture that use depthwise separable convolutions to build lighter neural networks. We also introduced two simple global hyperparameters that efficiently trade off between latency and accuracy. These hyperparameters allow the model builder to choose the right size model for their application based on the constraints of the problem. So basically, their objective is to make neural networks much lighter and portable for mobile and embedded vision applications. And they're going to primarily do this by using depthwise separable convolutions, and they're going to introduce two global hyperparameters that can trade off between the speed of the model and the accuracy of the model. And finally, they say that we present extensive experiments on resource and accuracy trade-offs and show strong performance compared to other popular model on ImageNet classification. So ImageNet is a very popular dataset that researchers use to benchmark their results against each other. And then we finally demonstrate the effectiveness over a wide range of applications, including object detection, classification, face attributes, and large-scale geolocalization. So basically, their architecture can be used for many different use cases. So the introduction is just going over the core idea and the motivation, which is im- which is making the model lighter while not decreasing accuracy significantly. So the paper describes an efficient network and a set of hyperparameters to build a very small low latency model that can be matched to the design requirements for mobile and embedded vision applications. And so these are the two hyperparameters that they introduce, which is width and resolution. So in the section 2, they go over some of the past work that has been done in this field, and this is common to all papers. They usually have the same outline. So this paper introduces a small network that the user can match his resource restrictions to. So if he wants a trade-off between accuracy and speed, he can decide how that trade-off should be, what should be more favored. And the MobileNet paper builds upon this exception network, which I'll cover in the future video. So stay tuned for that. And so here he just goes over some of the history that's been done in this, and he also says that there are other methods of optimization such as quantization, hashing, pruning, etc. But he doesn't go into those in this paper. So finally, let's get into the mobile net architecture. So the primary thing that he uses is depthwise separable convolution. So let's see first what a regular convolution is. So in a regular convolution, suppose this is our input. So our filter would be a decay into m size filter that is basically a block that you superimpose on your input, and then you calculate the dot product of all of the overlapping components. So what you're doing in a regular convolution is that not only are you capturing the details inside one channel, like in this channel, but you're also capturing how those details correlate to every other channel. So you're capturing two things: the relationship inside a channel and the relationship between channels. So depthwise separable convolution aims to break this into two parts. In one of those parts, you'll basically capture only the relationship inside one particular channel, and then finally you'll find the relationship between the channels. So this is what depthwise convolution filters look like. So instead of just having one filter, one three-dimensional block, you have two such filters. One of them is decay times decay, which is the filter size, and it only goes through one channel at a time. So basically what you do is that you take one of these filters and you just apply it on one channel. Then you take the second filter and you apply it on the second channel, the third filter on the third channel. So you're independently finding the relationship inside each channel. After you've done that, you stack these layers into uh, another block, and then you apply this filter. So what this is that this is the 1 into 1 into m, and as you can see, you will have m channels as the output of this convolution. And so you're finding out how this one pixel is related to every other pixel that comes behind it. So let's look at this in a little more detail. Alright, so let's get back to the paper. We were at section 3, MobileNet architecture, and he introduces here the depthwise separable convolution. So he says for MobileNets, the depthwise convolution applies a single filter to each input channel. So as we saw, we apply a single filter to every individual channel, and then the pointwise convolution applies a 1 into 1 convolution to combine the outputs of the depthwise convolution. So what does he mean by depthwise and pointwise? So he just called this the depthwise convolution and this the pointwise convolution. And also when he says we apply a 1 into 1 convolution, he actually means 1 into 1 into m. So he's not mentioning the m over there. And he says consider a standard input of df into m. So this is our input size, and this is our output size of one convolution. And so first he goes over the case of a normal convolution, because you want to compare how the depthwise does to just a regular convolution. So he says consider a kernel size of dk into m into n. So this means that there are n dk into m channels. So this is the number of these filters. So let's go a little bit more detail into the analysis of a regular convolution. So let's try to calculate the number of operations I would have to do in a regular convolution. So remember, the number of operations that I have to do for this block is the dot product of every overlapping pixel, right? So let's calculate the entire thing. So if I have a block of dk into m, I will do dk squared times m calculations for this block here, and then I slide this block across the width and the height, and I want my output to have the same dimension as df. So I'll do df calculations across the width to give me a width of df, and I'll do df down the height. So that'll be times df squared. And remember, I have n such filters. So whoops, I have n such filters. So I'll multiply this entire thing by n, and that's exactly what he has here. So yep. So he says the standard convolutions have a computational cost of dk squared dk squared times m times df squared times the number of filters. Alright, so now let's see what's so special about depthwise separable convolution. Alright, so remember that one of these is one of each, right? So let's go back to the drawing board right here, and let's try to calculate how many operations we do for this first layer. So for one of these, we're going to slide it across every individual channel. So one of these, let's say this first one will do dk squared. Oops, will do dk squared times the height and the width of our input channel, which is df squared. Oops, times df squared, and we have m such filters, so we'll be doing this m times. All right, and now let's see how. So when we do this, our output we'll be applying dk to all of these, and our output will be m dimensional. So this will be our output, right? And now we are applying these. So this has 1 into 1, so each of these has m. Each of these has m variables, and we're doing this again times the height and the width, and we have n of these. So these are the number of operations we do for this convolution, and so the total number we do is just the addition of both of these, and in fact that's what he's given right here. So he says that the depthwise separable convolution costs dk squared times df squared times m plus the cost for the pointwise, which is m times df squared times n, right? And so now he takes the ratio of the operations that we do for depthwise separable and for just the regular convolution. So as you can see, he's divided them, and this is the ratio that he gets. So we see that MobileNet, which uses 3 into 3 depthwise separable convolutions, uses between 8 to 9 times less computational power than standard convolutions, with only a small reduction in accuracy. So this ratio causes a massive decrease in the number of computations that we have to do for one single convolution layer. Alright, so let's just look at depthwise convolution with a tiny more detail. I will go over this in more depth in a future video, probably the exception paper. So let's go over. Yep, so this I found very interesting. Alright, so this is our first depthwise convolution. So we apply a filter for each channel, we get this. Now we combine these to produce one filter over here, right? So now the combination of this will produce 1 pixel here, this will produce 1 pixel here, and so every pixel on now this one input channel represents information from the entire depth, right? The entire depth of our original image. So now when I apply a depthwise convolution to this block, I am actually finding the relationship between a combination between my entire input width. So on my very first depthwise convolution, I will just be finding the relationship between each channel, right? There's no intercorrelation between these, but after I've done one pointwise, this 1 pixel encodes all of the information in the depth. So uh, I'll go over this more in another video, but this is a point that I really missed the first time I read this paper. So let's move on, go back to the paper. And all right, so now he just explains different parameters and different style choices that he made to get the best out of his model. So all layers are followed by a batch norm and ReLU. So in a regular convolution, normally you do the convolution and then you have a batch norm and ReLU. Here, since you've broken it up into two parts, he uses a batch norm and ReLU uh, even in between the parts. So he doesn't do both of them consecutively. He just does it twice. And then he makes some other style choices like RMS prop. He doesn't use data augmentation, no weight decay. So this is his entire MobileNet architecture. And so initially his input size is 224 by 224 times 3, and he applies this filter and he gets this output. So as you can see, the stride is 2, so the output will shrink into half. Then he does one depthwise convolution, so it stays the same. Then he does a separable one, and he has 64 channels, so the width becomes 64. And then he does another depthwise, then another separable, and he keeps on doing this, and this makes up his entire model. So his first layer he mentions here is all layers are depthwise separable except for the very first layer, which is a full convolution. So this is a full convolution layer. Now, all right, so I spoke about the hyperparameters that he mentions initially, and this is the second method that he introduces to reduce the computation load of the model. And so basically what he does over here is that he multiplies the number of input channels m to become alpha m. So alpha m is a number between 0 and 1. So basically what he does is that instead of having m channels, he has alpha m, so like half of m or 0.75 m. So the number of channels in the output that this produces decreases, so the models become lighter. So this is the number of computations with the alpha. And he also has a resolution multiplier, which is the second hyperparameter. So this is basically what it does is that if your original image size is 224, now it becomes 192. So basically let's say your p value is 0.78, right? So you multiply your input size to 244 by 0.78, and the image that you would actually consider would be 192 pixels. So this is something that's commonly used in unsupervised learning. For many cases, I wouldn't say image detection, but like denoising, changing the contrast, a lot of things. It doesn't matter what your image length and width are, because you're just finding patterns, you're not detecting an object. So for many cases it really doesn't matter what your input image size is. For some it does, like image detection, but he shows that even with variation of p, he gets pretty good results. So this is basically the entire all the adjustments that he makes up to this point, and then it's just showing the results of the model, changing the hyperparameters. So over here you can see that with a regular convolution network, it has 29.3 million parameters, and it achieved the accuracy of 71.7% on ImageNet, while MobileNet has just 4.2 million parameters, and the accuracy just decreased by 1%. And then over here he shows how the accuracy varies with changing the width multiplier and the resolution multiplier, so changing the input image size. And so he's basically trying to give the model builder the option about how they want to allocate their resources, and so they can choose, between what width multiplier or resolution they want, and how much they're willing to trade off depending upon their computation availability. So he's shown the results for that, and there's a very large reduction in parameter size and even uh, computation numbers. So that's basically the results part. And yeah, he shows his results for different data sets and different types of tasks. So this is a face attribution, and this is a geolocalization, object detection, face embeddings. So yeah, so we proposed a new model architecture called MobileNets based on depthwise separable convolutions. We investigate some important design decisions leading to efficient model. We demonstrate how to build smaller and faster mobile nets using the two hyperparameters by reasonably trading off accuracy and size. We compare different mobile nets to the popular models, and finally, a next step would be for them to release a TensorFlow model, which they have done a long time ago. So that's the entire paper. So hopefully you got a good idea about what mobile nets are, and you got more comfortable with research papers. So thank you.